In this section, we're going to learn about square roots. All of the ancient civilizations were well aware of the concept of square roots. Babylonians, Egyptians, Indians, and Chinese all knew how to extract square roots. Definition: square root of a number a is a number y such that y squared is equal to a. Finding the square root of a number is an inverse operation of squaring a number. Right, so the symbol, you're probably familiar with that. I mean, we've used it a few times. An example that you might have is something like 3 squared is equal to 9. The act of taking the square root extracts the 3, right? And symbolically, we would represent that as radical 9 being equal to 3, right? Perfect squares, we've talked about this a little bit, but the idea is that if you take a whole number and square it, the result of that would be a perfect square, something that is square rootable. Methods for finding square roots. We could use an interpolation method, process that approximates the value of a square root of any number using the square roots of perfect squares. Right? So we're basically looking to squeeze the decimal in between two known perfect squares. So find two perfect squares, one smaller, one larger than a given number. And oftentimes it's just a matter of one unit, one base unit in either direction. All right, I'll show you an example of that in a second. We can calculate the x value, x minus a squared, and b squared minus a squared. Right, and I'll kind of justify that in a sec. To get a ratio of d, that which gives us the relative distance of x between a squared and b squared. That's probably the trickiest part of the whole thing, right? Since x lies a relative distance d away from the point, away from a squared to b squared, it follows that radical x lies a relative distance of the way from a to b, which can be geometrically proven using similar triangle. Okay, so therefore we would say radical x is equal to the square root of a squared plus d, or radical x is equal to, or so not or as in a choice, or another way of saying it would be radical x is equal to a plus d. But the whole thing is like, okay, so where are we getting the d from? Where's the a coming from? That's probably the more confusing part of this, right? So we're looking to figure out how far away from that perfect square value the true radical is, right? So that's really what the crux of the whole thing is, and you'll see in the example. So we find two perfect squares, right? So, and that requires a little bit of either computation, or we'll call it number sense. If you know generally some perfect squares, then you would say, all right, well, radical 136 is between 121 and 144, 11 squared and 12 squared. Right, but we come up with that relationship. Right, so the a value is going to be 11, making the a squared value equal to 11 squared, which is 121. We're finding the distance from the given number, the one we're trying to find the square root of. We're finding the distance between that number and the lower bound. And then we're finding the distance from that upper number and the lower bound, the upper bound and the lower bound. The idea being that if we could figure out the ratio of that distance, they said using similar triangles, but if I were to say that you have some point, and this is kind of a repeat of the diagram up here, but maybe just looking at particular numbers, it'll make a little bit more sense. Right, so I have 121 down here. I have 144 over here. And somewhere in between, I have the 136. Because they're particular numbers, I can try to put it in a reasonable location, but that's it's not always going to be the case because if we're trying to generalize this to other numerical values, it could be kind of tricky to think of it that way, right? So we kind of look at it like that, but then kind of off on the side here, we look at it, and I'll try to do it with a diagram. I'm going to duplicate. I'm going to shrink it down because it'll be on a smaller scale. We're looking at the radical values. Radical 121, radical 136, and radical 144. All right, so this is this is to that, kind of like an analogy question. This is to that as that is to that. So I'm looking for the ratio of the difference between these two. So this distance here, that would be, that's where the 15 comes from. So actually, let's get rid of the question mark there. I'll just say 15. And then this overall distance here, which would be 23. So it's a 15 to 23 ratio. All right. So if I'm looking at it from the perspective of the 121, if I want to get to the 136, I have to go 23rds of the way from 121 to 144. All right. So in that context, hopefully it kind of helps to maybe not even context is the right word, but it's more like in that way of visualizing it, and hopefully it makes a little bit more sense. But what this is really saying is that this would have that same ratio. All right. So when I get my rule here, which is radical x is equal to radical a squared plus d, right? That d being the ratio value. All I'm doing is taking whatever my a value is and adding to it whatever that ratio is, right? And that would give me the approximation of the radical value, right? So again, it's really kind of looking at it as 136 is 15 23rds of the way from 121 to 144. All right. And so that's the same idea by saying that I'm going to apply that same ratio value, but on a smaller scale. All right. So my radical 136 would be equal to the radical 121 plus that ratio of 15 23rds, right, of a single unit essentially, right? It's just a unit is more broadly from 121 to 144, but that's, I'll say, if we're talking about like 23rd, halfway of that would be 11 and a half. So a little bit more than halfway from 121 to 144. So this would be a little bit more than halfway from radical 121 to radical 144. So we add on that extra value. So that gives us 11 plus 15 23rds, which gives us the 11.6522. I'll type it in anyway, but. All right. Now, if I type in the square root of 136, I get something, and it's not quite, but it's close enough. If you're looking for a decimal approximation, a reasonable approximation, that would be good enough to get you there. I mean, if I'm rounding to the nearest tenth or the nearest whole number, it would round to the same value. All right. You could also check by going the other way, taking your answer and raising it to the second power and seeing how far you were off. All right. In this case, it's not too bad. All right. So same idea in the second one. So I have radical 41 that's going to be less than one radical that we know and greater than another radical that we know, right? So if I'm looking at perfect squares, because in that previous example, if it feels like you kind of pulled it out of, or we pulled it out of thin air, like where the 121 and 144 come from, it comes from the idea that if I take a whole number and square it, the result will be a perfect square. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36 is 6 squared, and 49 would be 7 squared. I could keep going, but I have two values, one that is below the one in question and one that is above the one in question. Right, so that's my 36 and my 49. Right, so my A value is, the square root of 36. So my A is 6. Right, my B value would be 40, the square root of 49, which would be 7, but we don't really need that because what I'm doing to find my D, my the ratio of displacement, if you will, that's going to be equal to the 41 minus 36, and then the 49 minus the 36. All right, so it's really saying the distance from 36 to 41, which would be 5 units, and then the overall distance, which would be 13 units. All right, so my radical 41 is going to be equal to 6 plus 5 over 13. And we get about, if I go to 3 decimal places, 6.38, it didn't, 4 decimal places, so 3846. All right, now if I take that actual square root, I see that we'd round to the same number. Instead of 6.3846, if I'm going to the nearest tenth, I would say 6.4. So I'm right in that correct neighborhood. All right. So again, it's really just a matter of kind of scaling things down. It's a relative distance between values. So just going back to that diagram real quick. If I have my two numbers, so just call it a little bit of a recap here. My radical 36, my radical 49, and somewhere in the middle is going to be my radical 41, right, a little bit closer to the radical 36. Right, I'm looking at this relative distance here compared to this relative distance here. All right. So by finding, and honestly, you don't even really need to, if you want to use a little bit of a variation on the formula, you could look at the radical values themselves. It's just the numbers get so funky, and we're trying to kind of live in the world like a pre-calculator sort of world. So kind of working with radicals without working with radicals is sort of what we're trying to do. All right, but if I wanted to, I mean, technically I could say I'm looking for the distance between radical 41 and radical 36 over radical 49 and radical 36. But then I would have to simplify radicals in order to figure out an approximation of a radical. So that's the idea behind why we would scale it up. And, the diagram's not going to be to scale, but instead of working with the square root values, I'll work with the square of the square root values and find those relative distances, create a ratio out of it. And if I tell you that this ratio here, small to big, has to be the same as this ratio here, small to big, then that kind of gets you there in terms of the concept behind it, I think.